Welcome to our series on RAG, Retrieval Augmented Generation. We're experimenting with new ways to teach AI. First one is using popular storylines to make complex concepts stick. We really want to know, is this working for you? Whether it's too simple, too dense, or just right, your feedback helps us improve. Leave a comment with your thoughts, what works and what doesn't, or perhaps suggestions for future topics. If you find this helpful, don't forget to like and subscribe.
Welcome everyone to this deep dive into the next generation of Retrieval Augmented Generation systems. The title of our presentation is Beyond Flatland, the RAG system's next evolution. If you are familiar with the classic novella Flatland, you know it describes a world constrained to two dimensions, unable to perceive the richness of the third. Right now, most traditional RAG systems operate in a kind of flatland. They see the world only through text embeddings and keyword matching. They are excellent at analyzing strings of words, but they are fundamentally blind to visual data, complex relationships, and intricate data structure. This limitation prevents them from solving the most complex, real-world enterprise problems where information is inherently messy and multimodal. Today, we are going to explore exactly how RAG is breaking free of these constraints. We are adding new senses to our agents: sight, connection, and ultimately, sophisticated reasoning power. We are transitioning the RAG architecture from simple text retrieval to comprehensive knowledge navigation. This journey involves two major and simultaneous evolutions, integrating true multimodal capabilities and leveraging the explicit structure and power of knowledge graphs. Let us begin by defining the core problems that these new systems are specifically built to solve. Our hero, the typical text-based RAG agent, is metaphorically trapped. It exists in a world made purely of text strings, and this limitation manifests in two critical ways that define the boundaries of current systems. The first core limitation is visual blindness. It can't see. Imagine trying to assemble furniture using only a verbose, wordy description of the manual, never actually looking at the diagram itself. This is what we call the IKEA Manual Problem. The agent might successfully read the instruction, "Please locate part 402, but if the part itself is only visually represented in an architectural schematic or an assembly diagram, the agent cannot interpret the image itself. It is relying entirely on simple text extraction, or OCR, which is fine for pulling out letters, but completely fails to understand spatial relationships, connecting lines, or complex layouts. The second, equally crucial limitation is the inability to connect disparate facts or concepts. It can't connect. Look at the block of code on the right. The agent sees CEO and supplier as two separate, high-dimensional concepts based on word proximity. It understands the words individually, but it misses the crucial relational information, established in an adjacent document, which explicitly states the CEO is the key reviewer for the supplier contract. Standard vector search finds semantic similarity, but it almost never finds structural connection. As the quote summarizes, we are attempting to describe a visual or structural problem in words, and the agent is searching a text database, which is a fundamental and limiting mismatch we must aggressively address. To solve the initial problem of visual blindness, our hero must fundamentally unlock a new sense: the power of sight. This is the essence of building truly effective multimodal RAG systems. When we talk about processing documents in the modern enterprise, we are no longer just dealing with pure, easily digestible text files. We handle complex slide decks with embedded charts, intricate architectural blueprints, detailed operational manuals with flow diagrams, and dense screenshots from proprietary software systems. The key architectural shift here is moving far beyond simple text extraction, or OCR. OCR can pull out words, but it cannot understand the context of those words within the overall image structure. Genuine visual understanding means perceiving the entire layout of the page, recognizing that a specific numerical label belongs to a specific graph axis, or identifying an icon as representing an entire complex process. Multimodal models give our RAG systems the eyes they need. By simultaneously encoding visual information into the exact same mathematical space as text, we allow the system to search for visual concepts using natural language. This dramatically expands the universe of documents the RAG system can effectively process and retrieve from, transforming it from a mere sequential document indexer into a comprehensive knowledge perceiver capable of processing diverse input forms. This capability is the first major pillar in moving beyond RAG Flatland. So, how exactly do we achieve this feat of giving RAG systems true sight? The underlying technical answer lies in the creation of what we call the Joint Embedding Space. This space acts as the bridge between worlds, unifying text and visual data. The mechanism relies on powerful foundation models, such as those inspired by CLIP, which are trained to learn a shared, unified mathematical language for both images and text simultaneously. Essentially, these models project both data modalities into the exact same high-dimensional vector space. This unified projection is crucially important because, in this shared space, concepts that are semantically similar are intentionally mapped close together. The result is elegantly simple yet profoundly powerful. The vector representing the text concept of a dog becomes instant neighbors with the vector generated from a specific picture of a dog. We can now use words to find pictures, or use pictures to find related descriptive documents. Consider a practical enterprise example. If a manufacturing technician issues the query, flashing red light, the resulting vector will naturally land adjacent to an image of a specific dashboard warning light in a proprietary manual, even if that image contains no text describing a flashing red light. The model understands the pure visual meaning of the picture and its immediate semantic connection to the query, providing superior retrieval accuracy. Now let us look at how all these powerful pieces are correctly fitted together into a cohesive architecture, forming the multimodal pipeline. The entire process begins with ingestion, specifically the split. A document, perhaps a complex PDF, is ingested, and a sophisticated layout parser separates the raw text from the non-textual elements such as images, detailed charts, and tables. It treats them as distinct, yet interconnected, chunks of information. The second phase is embedding. Text chunks are sent to a specialized text embedding model, while the images are routed to a visual embedding model. Crucially, as we just discussed, both models project their respective data into that shared joint embedding space. In the storage step, all these resulting vectors, regardless of whether they originated from text or a visual asset, are stored together in the same vector database, maintaining the links back to their original document chunks. When a user asks a question, the retrieval step occurs. The text query is vectorized and used to find the most similar vectors, which might retrieve pure text context or relevant images. Finally, we reach the generation phase, powered by a vision language model or VLM. The retrieved text is passed directly to the LLM, but if an image is retrieved, it is passed to the VLM along with a prompt. This prompt explicitly instructs the VLM to interpret and explain this specific image in the context of the user's original question, allowing the system to derive context from all available modalities for a complete answer. If multimodal RAG is about unlocking sight, then the highly complex data table is often considered the final boss of RAG. Tables present a severe and unique challenge because their meaning is fundamentally both visual and textual. Their intelligence lies not just in the words within the cells, but in the visual structure that defines headers, merges, and groupings. Traditional RAG systems usually attempt what we call Approach A, the text approach, which tries to convert the table into a flat textual structure like Markdown or CSV before embedding. This strategy is extremely brittle and fails catastrophically when dealing with complex layouts, such as tables featuring merged cells, nested hierarchical headers, or irregular cell spanning, leading to a profound loss of critical structural context. The state-of-the-art solution, which is central to the evolution of advanced RAG, is Approach B, the vision approach. Here, we snapshot the table as an image and let a powerful vision language model, or VLM, handle the deep interpretation. The VLM does not just read the text, it simultaneously deciphers the visual structure and the meaning directly. It understands that a merged header spans 3 distinct columns, or that a specific numerical row entry relates to a particular column header visually, not just linguistically. This integrated visual intelligence is the only reliable way to accurately extract the complex hierarchical and contextual information trapped within highly formatted data tables, which is particularly vital for financial or engineering documents. Now that our hero has successfully acquired sight through multimodal RAG, we face the next, deeper challenge. Sight alone is not enough, because understanding the world requires understanding causality, structure, and explicit connections. Our hero's understanding, while visually rich, remains superficial in terms of relationships. It knows what things are, but not how they dynamically relate across a large document set. Look at the illustration again. Our current vector search finds similarity and proximity. If a user queries for lithium, the system easily retrieves documents related to lithium components, and it also finds documents like the Product Line X manual because the words often occur together in the embedding space. The vectors are close neighbors because the semantics are similar. However, vector search fundamentally fails to trace a complex, multi-hop supply chain path. It cannot logically trace the sequence. Lithium is part of a battery, which is used in Model X. This level of reasoning requires logical, multi-hop inference that similarity search simply cannot provide. We need a robust, formal mechanism to encode explicit, directional relationships into our knowledge base, moving beyond the fuzzy, probabilistic connections of vector space. We need structure, and that structure is found in graphs. To formally address this missing link and solve the connectivity problem, we must fundamentally evolve our architecture from similarity to connectivity by implementing GraphRag. This represents a paradigm shift where we transition from a world of what to a world of how. We move away from the vector space, which is best described as a cloud of concepts, to the knowledge graph, which is a structured universe of relationships. In vector space, concepts just float near each other based on concurrence probability. In a knowledge graph, we introduce explicit hard-coded structure built on two precise components, nodes and edges. Nodes are the entities or objects, which could be people, products, places, or concepts, such as Tesla, Elon Musk, or Model X. Edges are the relationships that explicitly connect these entities, such as CEO of, supplied by, manufactures, or part of. This structure captures the verifiable, hard-coded facts of the world, defining exactly how one entity influences or connects to another entity. If we ask the graph a complex question like, what does Elon Musk manufacture that uses lithium? The graph can trace a precise path. Elon Musk is CEO of Tesla. Tesla manufactures Model X. Model X uses batteries, and batteries contain lithium. This is not probabilistic guessing. It is precise, verifiable, and structurally sound reasoning based on the established, encoded map of the world. This capability is absolutely essential for complex analytical questions. Historically, the biggest barrier to widespread adoption of knowledge graphs was the initial construction process. Building these incredibly precise knowledge maps was a painstaking, often incredibly painful manual process requiring highly specialized data engineers and knowledge curators. This laborious process was the main reason graphs remained niche. However, the rise of large language models has completely revolutionized graph creation, making it scalable and automated. Today, we effectively use the LLM itself to construct the map for us dynamically during the data ingestion pipeline, transforming the LLM into the graph architect. The process is now elegantly streamlined into 3 steps. First, we read a chunk of text, for example, Steve Jobs co-founded Apple in 1976 with Steve Wozniak. Second, the LLM extracts the essential structured information using sophisticated prompt engineering. It identifies the entities, Steve Jobs and Apple, and the specific directed relationship between them, co-founded. The LLM outputs this crucial structured triple, Steve Jobs co-founded Apple. Third, we store the entities and their new relationship in a specialized graph database, such as Neo4j. As we ingest millions of documents, the graph grows organically, building a massive, interconnected network of knowledge derived entirely from unstructured data. This automation is key because it means we can instantly turn raw text data into a structured, searchable database of facts, ready for logical navigation. We have now introduced the 2 crucial revolutionary components, multimodal capabilities and knowledge graphs. The most advanced RAG systems today realize we no longer have to choose between them. We must combine both in a powerful new architecture called hybrid RAG. This approach represents the synthesis, the best of both worlds. This architecture brings together the strengths of 2 distinct retrieval mechanisms. On one side, we have vector search, providing fuzzy semantic understanding, which tells us the what. This is excellent for quickly finding neighborhoods of relevant documents based on meaning and similarity. On the other side, we have graph traversal, providing precise, logical navigation, which tells us the how. This is absolutely necessary for tracing chains of causality and establishing verifiable links. Hybrid RAG is the architecture that successfully combines the semantic discovery power of vectors with the precise, logical navigation of graphs. This structure particularly excels at complex multi-hop reasoning. It can answer nightmare queries that are functionally impossible for pure vector search, queries that require tracking specific entities across multiple documents and relationship types. For instance, consider the challenging question: did any investors in Company X's Series A also invest in their key competitors? Answering this requires a sequence of precise relational jumps, which can only be achieved through graph traversal, initiated by a vector search entry point. Let us conclude by walking through how our hero, the hybrid RAG system, navigates a complex analytical query quest using this fused architecture. The entire process follows 3 essential steps. Step 1 is vector entry, or find the neighborhood. The user asks a question, and the system first uses its semantic vector search capability to find the most relevant starting point within the underlying knowledge graph, such as the node representing Company X. This leverages the semantic power of the LLM to identify the subject of the query, regardless of exact keyword matching or phrasing. Step 2 is graph traversal, or navigate the streets. Starting from that initial entry node, the graph engine intelligently explores the connections, moving several hops away, tracing relationships like invested in or competitor of. This is where the powerful benefit of the graph emerges. The traversal might find related documents and information, such as the names of key investors or subsidiary contracts, that share absolutely no keywords with the original query, but are structurally and logically linked. The graph engine dynamically plans the most relevant path to answer the precise question, essentially conducting a rapid, structured investigation. Step 3 is context construction. Once the traversal is completed and all relevant nodes and their associated documents have been identified, the system gathers all the specific evidence, including the text snippets, visual charts, and table chunks found along this structured path. This highly curated, logically derived set of evidence provides the comprehensive, verifiable context necessary for the final large language model to generate a precise, accurate, and structurally sound answer. We have completed the ambitious journey beyond Flatland, and the result is the emergence of a new form of intelligence within our AI systems. The steps we have taken are foundational to mimicking real-world human cognitive processes. With multimodal RAG, we successfully gave our RAG system the crucial sense of sight, allowing it to interpret complex visual data like charts, blueprints, and structural tables, integrating them seamlessly into the knowledge base. This overcomes visual blindness. With GraphRag, we instilled an understanding of explicit, directional relationships and complex structure, moving past mere semantic similarity to structural logic and traceable causality. We have fundamentally moved far beyond the previous generation of RAG, which was often simply described as a basic open book exam, where the AI just searches a flat index for keywords. Our new integrated systems are actively simulating a complex, unified cognitive process that integrates both perceptual input, meaning visual perception, with structural logic and advanced relational reasoning. This comprehensive approach leads to far more accurate, contextually rich, and highly verifiable answers, empowering AI to tackle genuinely complex analytical challenges previously reserved only for human experts. Mastering these new multimodal and graph-integrated RAG powers is only the beginning of the next phase. The next great adventure and major technical quest is transitioning this cutting-edge research into robust, reliable production systems that can handle real-world scale and enterprise load. The next focus involves successfully deploying, managing, and scaling these complex architectures effectively in the real-world environment. This introduces an entirely new set of engineering challenges focused specifically on efficiency, cost management, and system reliability. Specifically, we must tackle the hard reality of running these complex, multi-stage systems in large-scale production environments. This means diving deep into LLM ops, establishing resilient deployment and monitoring strategies perfectly tailored for multimodal pipelines. It also means mastering advanced caching techniques, which are absolutely essential for managing the latency and cost associated with frequent calls to multiple embedding models and resource-intensive vision language models. And finally, we must closely analyze the economics of serving this advanced AI at scale, ensuring these highly powerful systems remain both performant and cost-effective for broad adoption. So, while we have achieved a breakthrough in architectural design, the operational challenge remains significant. Join us in our next session where we will explore these practical production realities.